So what if I told you that a massive river system could actually be valued just like the battery in your phone? Today, we're going to tackle a really fascinating puzzle. How do you put a price tag on stored water? We're going to explore this really clever analogy that connects a river to an electrical wire to figure it out. So let's dive in. So this is the big question, right? Canada holds back 15 million acre-feet of water on the Columbia River. And just so you know, that's enough water to cover 15 million acres of land 1 foot deep. So what's the actual dollar value of all that stored potential? See, it's not just water, it's a massive strategic asset. And just to give you a sense of the scale here, that 15 million acre-feet, it's about 10% of the entire Columbia River's annual flow, all of it held in reserve. I mean, that's an almost unimaginable amount of water. So how in the world do you even start to put a price on that? All right, so here's how we're going to break this down. We'll start with the river itself, then we'll introduce this pretty surprising electrical analogy, break down exactly how it works, and then use it to run the numbers and find our final price tag. Okay, first things first, let's get our heads around the physical reality of the Columbia River. You know, this isn't just some scenic waterway, it's an absolute powerhouse. Okay, get ready, because these numbers are just staggering. The system can generate up to 30 gigawatts of power, and to put that in perspective, that's like having about 30 nuclear power plants. Annually, it's cranking out up to 150 terawatt-hours of energy. And the key, the thing that makes all this possible, is that 15 million acre-feet of Canadian storage. The crucial point is this: the water is directly tied to a massive energy system. Okay, so how do we get from a river to a dollar sign? This is where things get, well, really creative. We're actually going to borrow some concepts from electrical engineering. And here it is. This is the big idea. By treating the entire river system like a giant electrical circuit, we can use the predictable laws of physics to model its economic value. It's an absolutely brilliant way to reframe the problem, making it something we can actually solve. All right, let's dig into the core of this model and see exactly how this analogy works. We're going to map electrical concepts directly onto economic ones. Okay, so check this out. Because the analogy is, well, it's almost perfect. Electrical current, that's your cash flow. Voltage, you can think of that as the market price, right? The pressure to buy or sell. Conductance is just how easily that value can flow. But the real game changer here for us is capacitance, the ability to store a charge. In our model, that's the stored value in the reservoir. So once you have that analogy locked in, you can start to see the reservoir for what it really is in this model: a giant water-based battery. Now, this is an absolutely critical idea. Think about it. A fully charged battery has value, right? Even if it's just sitting on your desk, not powering anything. Well, stored water is the same. It has immense value even when it's not flowing through a turbine. Its value is all in its potential. And to really nail this idea down, the source material introduces this fantastic term, vaultage. It's perfect, right? The water is locked away in a vault, representing all this stored economic potential, just like electrical voltage represents stored energy potential. And this chart just lays it all out perfectly. The reservoir holds the potential, the voltage. The river's flow, that's the current. And when a dam holds that water back, the potential is separated from the flow. It's like a capacitor in a circuit, just storing up all that value, waiting for the right moment to be released. Okay, we've got the framework. We understand the analogy. Now let's put it to work and actually calculate the value of all that stored water. You know, the logic is pretty straightforward. First, we figure out how much potential energy is in each unit of water. Then we translate that energy into a dollar value based on what electricity is selling for. And finally, we just multiply that by the total amount of water we've got stored. Now, this might look a little complex, but honestly, it all boils down to 3 key things. The most important one is what they call head, and that's really just a simple concept. It's how far the water falls from the top of the reservoir down to the turbine. The other 2 are just the efficiency of the turbines and, of course, the market price of electricity. Change any one of those, and the value of the water changes. All right, so let's run a quick scenario here. If we assume a pretty low head of, say, 100 feet, and a standard electricity price, the value comes out to about $4.59 per acre-foot. But now, watch what happens. When we crank up the head to over 300 feet, which is way more typical for a huge dam like Grand Coulee, look at that. Even with the same electricity price, the value per acre-foot more than triples to over 15 bucks. It just goes to show you the height of that battery makes a massive difference. Okay, we have all the pieces of the puzzle now. It's time to multiply these numbers by our 15 million acre-feet and answer our big question from the beginning. And here we go. This is the final price tag. Depending on things like the height of the dam and the price of electricity, the total value of that stored water ranges from a cool $69 million on the low end all the way up to a staggering $451 million every single time the reservoir is used. So yeah, that's the core finding right there. By applying this simple electrical analogy, we've turned a massive physical resource into a concrete financial range. So what's the big takeaway here? It's not just about the raw power. It's about the flexibility. This voltage basically turns the reservoir into a strategic financial tool. It lets grid operators act like energy traders. They can store power when prices are low and sell it when prices are high. And that strategic capability, well, that's where the real money is. And that really leaves us with one final big question. This whole model gives us a completely new lens to see the world through. It makes you wonder, if a river can be a battery, what other massive natural resources are we completely miscalculating? Just because we haven't found the right way to look at them yet.